Hello everyone, welcome to the course Data Structures. This is Thulasi Chitra, Associate Professor, Department of CSIT, MLR Institute of Technology. Okay. In this session, we will be discussing about what are the shortest path algorithms we have. Under that, we have some categories. In that, we are going to first discuss about Dijkstra algorithm, an example on Dijkstra's algorithm, and what are the drawbacks you are going to find with Dijkstra's algorithm. Okay. First, we'll see what is the shortest path algorithms we have. Here, the shortest path algorithms where we have are, in short, or we can represent this shortest path algorithms as single shortest source shortest path algorithms. That is, in short, we can represent it as SSP, triple SP, right? Under that, we are going to look into Dijkstra's algorithm and Bellman-Ford algorithm. These two algorithms we are going to discuss. And another one where we have is all pairs shortest path algorithms, that is nothing but APSP. This is nothing but which algorithm that comes under this is Floyd-Warshall. This is another algorithm where we are going to discuss under all pairs shortest path algorithms. Okay. First, we will be seeing about what is this Dijkstra algorithm, why we need to study about this Dijkstra algorithm. Why Dijkstra's algorithm is required to find the shortest path, right? Mainly, this is used to solve the single source shortest path algorithm. To find the single source shortest path, we are going to use this Dijkstra's algorithm. Now, finds the shortest distance between two vertices of a graph. If I am going to have a graph and it is going to find the shortest path between or distance between two vertices on a graph, right? And creates a tree of shortest paths from starting source vertex to all other points in a graph. Not only finding the shortest distance, it is also creates a tree of shortest paths from the source vertex to the all other points in the graph. In all other, from this, suppose I am going to consider this as a source. From here, it is going to find all other paths also, right? It works on both directed and undirected graphs, right? You know that we have graphs are of two types. One is directed and another one is undirected graphs. In directed graphs, you will be having the direction from one vertex to another vertex. In undirected graph, we don't have any direction. If I am representing a single path or line between those two vertices, that is nothing but an undirected graph. You don't have any direction. It is considered as bidirectional, right? And it differs from minimum spanning tree. As we have seen in BFS, DFS, we are going to find a minimum spanning tree, right? And here, this Dijkstra's algorithm is going to different from the minimum spanning tree representation. And this is similar to BFS. It is similar to BFS, but not finding any minimum spanning trees here, right? And gives optimal solution using greedy method. By using greedy method, it will be giving the optimum solution also, right? Now, what is this Dijkstra's algorithm is going to do? The main approach here we are going to use is a greedy approach. And what is the input this algorithm will take? It is going to take the weighted graph with the G equal to E comma E, E comma V. E is nothing but the edge and V is the vertex. And source vertex V belongs to capital V. That is, V is nothing but the vertex, such that all edge weights are non-negative. Here in Dijkstra's algorithm, all weights what you are going to represent for a graph are non-negative weights. Okay, that is the main input we need to give it for the Dijkstra algorithm. And what is the output you need to get? Lengths of the shortest path. You are going to get the length of each and every path or shortest path themselves from a given source vertex to all other vertices. From that particular source vertex to all other vertices, what is the path you are going to have? That will be given as the output. Let us take the real-time example where we can see here, or this may be mainly used in our Google Maps also. You can see the source here and destination here. This will be giving the shortest path between the source and the destination. If you have many different paths in between this, but it will be taking the shortest path and that will be giving as your destination. And a subway, which is also the shortest path between its source and destination, that one also it will show. It will also select that subway subpath and that will be considered as the shortest path. Okay, and you can see here. Consider this Dijkstra's algorithm will be working based on this relaxation. Now, before going to see that, here I am going to have 3 vertices. Now, I want to move from source to destination. In between that, I am going to have one more vertex. Now, to reach to 3, from 1 to 3, in between we have one more vertex also. Now, for this, what is a weighted graph, and the remaining, how I am going to find the weight for a particular vertex also we'll see, right? Now, for this one is named with U and this is V. The vertex is U and V. U to V you need to reach. Now, the weight of this particular path is 2, right? The weighted graph given from 1 to 2 is 2. Now, what is the weight for this 2? The weight of this one is 2. The weight for this one is 2. And based on the formula also, we'll see how we are going to find it out, right? And initially, this will be 0. Initially, the source vertex weight is 0 and 1 to 2 is 2. And so that we are going to find the weight of 2 is 2. Now, what is the weight of this one? Initially, it will be of infinity. We don't know what is the value of vertex 3. Now, how I can find the vertex 3 value? The distance of this one is nothing but, here we have 2. The weight of this one is 2. 2 plus 4 is nothing but it is 6. Now, how we could find all these values, right? Now, suppose for the first one, d of u is initially the vertex 1 is 0 plus cost of u comma v, this one, cost of u comma v. If I am going to reach here, in between that first I need to reach here. Cost of u comma v must be less than d of v. What is d of v here? D of v is nothing but infinity. And cost of u comma v is nothing but, here we have cost is 2, right? So, we are going to get d of v equal to u plus c of v is nothing but 2. So, we are going to get the value as this one as 2, right? Source to destination is 2 for up to here. Now, from here to here I need to find. From here to here I need to find. Now, what is your d of u value? D of u value is now 2 plus cost of u comma v is nothing but 4. Is less than, now d of v value is infinity. Yes, 6 is less than infinity. Now, I am going to take the minimum value. The minimum value is 6. So, I am going to replace the vertex weight with 6. That is, the distance what you have find is 6. Like this way, with this relaxation, we are going to work on Dijkstra's algorithm. Okay. Now, we'll solve one example based on this Dijkstra's algorithm. Let us see how this is going to work. The same relaxation method we are going to use here. Let us consider this is a graph where you have, and how many vertices we have? We have A, B, C, D and E. D and E are there, right? Now, here all the vertices are with the weighted graphs, that to be all positive values. You can see here you have 3, 10, 2, 1, 4, 8, 2 and 7 and 9. These are all the weights that was given for this graph. Now, first initial what we need to do is, we need to represent all the vertices in the row like this way. A, B, C, D, E, all the vertices we have placed, and we need to start from the source vertex. Source is here A. From source to destination we need to reach. But in this Dijkstra's algorithm, it has to find the value from source to all the vertices, right? So that we are going to start from A. Here its value is 0, and the remaining all values has to be placed with infinity, right? Source B, C, D, E, all values are going to be placed with infinity. Done. And here S is empty still. Still we have not visited any vertices, right? Now after this, now I started from A, right? Now I need to continue with the other vertices. So that what we need to do, I have selected A as the source vertex, and from there I am going to move. And initially we have all values are with infinity. Now from A to B, what are all the outgoing vertices, outgoing arrows? Consider outgoing arrows. Those values we need to place it in this tabular form, right? What are the values you have? 10 and 3. Those values are there for A to B and A to C. Now look here. A to B you have 10 and A to C you have 3. But in this, by using that relaxation formula, we are going to find the value of this one and this one. How we are going to find? D of U plus cost of U comma V. It should be less than D of V, right? If I am going to consider this path, D of U is 0 plus cost of this one is 10 less than V is infinity. Now 10 is less than infinity, so that I am going to replace infinity with 10. In the same way for this case also, D of U is 0 plus C of U comma V is less than D of V. Here also this is infinity, this is 0, and here the value is 3. 3 is less than infinity, so I am going to replace this minimum value to that particular node, right? Like this way we have find it out. After placing these values at that particular vertices, right? Now, which is the minimum among these 10 and 3? That has to be selected, right? Among this 10 and 3, 3 is the minimum value. 3 is the minimum value. Now, from there, you find out what are the outgoing edges you have. You have C2B is there, C2D is there, and C2E is there. These are the vertices, outgoing edges you have, right? Now, A to C we have reached. Already we have taken A, and A to C we have done. That's why we are placing those particular vertices into S. Now, in this minimum value is 3. So that I am going to select this C value, and from there, what are the outgoing edges that was there, that one we are going to consider, right? Now C2, let me check this diagram. Yes, from C to B is there, from C to D is there, and C to E is also there. Again, use the relaxation method to find the weights of each and every vertex. Now from C to B, you know that what is that formula? D of U plus C of U comma V is less than D of V, right? Now first D of U, from C to B I am going to check. C of this is 3, D of U is 3 plus C of U comma V. C to B, its cost is 4 less than D of V value is 10 actual. Now 7 is less than 10. 7 is less than 10. So we need to replace here. Previously we have 10. This has to be replaced with 7, which is having the minimum value that has to be placed. Okay, done. Now from C to D we will check. C to D you have D of U plus C of U comma V is less than D of V. Still we don't have any value here. Previously it was infinite. What is D of U value is 3 plus cost of this one is 8. 8 plus 3 is nothing but 11. 11 less than infinity. Yes, 11 less than infinity, this is the minimum value. So previously it was infinity, now we are going to replace with 11. Now C to E, in the same way, D of U plus C of U comma V is less than D of V. What is C? This value 3 plus cost of this one is 2 less than D of V value is, previously it was infinity, right? Still we have not replaced anything. Previously it was infinity, right? Now this is 5 less than infinity. So I am going to replace infinity with 5. Now place all these values in the next row. Here we have 7. Then we have 11 at D, and E we have 5. Right? Like this way we need to find all the values. After finding all these 3 values, right? After finding all these 3 values, now we need to do what? We need to check for the smallest value. We need to check for the smallest value. 7, 11 and 5, right? Among these, 5 is the smallest. Among this, 5 is the smallest. That is, we are going to select the vertex E. From E, what are the all outgoing edges you have? From E, you have E to D, only one value is present. Here, we are going to select the minimum element, that is 5. 5 is the minimum value when compared with 7, 11 and 5. Right? Based on that, we are going to select the vertex E. Right? From E, which are all outgoing vertices or edges we are going to check. Now from E to D, we have only one outgoing edge, so that, or check for the relaxation, right? Now what is that? D of U plus C of U comma V is less than D of V. What if D of U value is 5 plus cost of this one is 9 less than, here already we have 11. But here you have 9 plus 5 is nothing but 14 less than 11. But 14 is not less than 11. So that we are going to place with the same value, that is minimum value is 11, we are going to place as it is. Right? We are placing at D 11 as it is. Now among these two, 7 and 11, which is the minimum? Minimum is B. Minimum is B here. From B, if I am going to select, B, what are the outgoing edges you have? B to C is there and B to D is there. Now find the cost. D of U plus cost of U comma V is less than D of V. What is D of U value for B? Is 7 plus cost of this one we will see. B to C we will see. 1 is less than D of V value is 3. 7 plus 1 is 8. 8 less than 3. No. So we are going to place only 3 as it is. We are going to place 3 as it is. We don't find any much more change here. The same 3 will be there. Next one. D of U value is nothing but 7 plus cost of U comma V is 2 less than D of V value is 9. 9 less than 9. No. It will be the same value. So I am going to replace with, sorry. Here you have actually 11, it is not 9, it is 11 previously it was. Now, so it will be replaced with 9, 9 will be replaced from 11, right? Now, I am going to have, instead of 11, I am going to get the value as 9, right? These are the values, this is the way where you can reach from source to destination. We have A to C, C to E, E to B and B to D, right? This is how this Dijkstra algorithm will work. And what is the disadvantage we are going to find with Dijkstra's algorithm? The main limitation for Dijkstra's algorithm is that it does not work correctly with the graphs that have negative edge weights. Up to now, we have seen all positive edge weights. But if you are going to have the negative edge weights, in that particular case, this algorithm won't work properly. In fact, if there are negative weight negative weights in a graph, Dijkstra's algorithm can give incorrect results or even go into an infinite loop also. It is keep on changing the values of all the vertices, keep on changing. It won't stop anywhere, right? Or sometimes it may give some incorrect results also. This is the disadvantage you are going to find with Dijkstra's algorithm. And moral summary of this session is, we are going to have the shortest path. We have discussed about what are the shortest path algorithms we have, and the other one we have seen about the introduction to Dijkstra's algorithm and why we need to study about the Dijkstra's algorithm, and we have seen the example on how we are going to find the shortest values or shortest distance between each and every node from the source, and we have looked into the drawback of Dijkstra's algorithm also. I hope you understand this concept. Thank you.